All right, this is a big important point. We are talking about buoyant force. All right, so the image we have in front of us isn't so very different from the image we had with the cube of water underneath the water. But this one is a cube of, it's not a cube, it's a cylinder of something else. Maybe it's a metal, maybe it's a piece of wood, we don't know what it is. But it's something beneath the surface of the water. And for our purposes, we're just looking at it at this instant in time. It may sink or it may float, but right now we're just looking at it at this position underneath the water. All right, so what do we know? We're going to call this thing buoyant force, so the F sub B is buoyant force. And what it is, what we're talking about here, isn't the net force on the object, it's just the buoyant force. What is the water? What is the fact that this thing is submerged in a fluid? It doesn't have to be water, it could be oil or corn syrup or something else, or it could be air, the air that we're surrounded by in the room. What does the fact that it's submerged in that fluid mean for the upward acting force on it? So net force in the y-axis is force up minus force down. We're not talking about net force, but we're talking about the force up, P2A, minus the force down, P1A. So P2 minus P1 equals rho GH. Hey, I remember that from our last discussion. So here we go. FB equals rho GHA. Hey, H times A is volume. FB equals rho VG. Now listen carefully because this is an important concept. The buoyant force, the force that acts to push this object up inside our fluid, is the density of the fluid times the volume of the object times G. And it turns out that what we're talking about is the weight of the fluid that is displaced by virtue of this object being in the water. A conceptual thing to think about: if you have a beach ball and you're at a swimming pool and you pull that beach ball under the water, you can feel a huge amount of force pushing it back up. Why? Because that beach ball doesn't have very much weight, but when you shove it under the water, it's displacing a lot of water, maybe up to a cubic meter of water, which in that case has a huge amount of force. If you've ever tried to carry a gallon jug of water, maybe a couple, 3 or 4, you can imagine that that's a lot of force, that's a lot of weight, those things of water. So when you displace that much water, that's how much force is being pushed up. So Archimedes' principle states any fluid applies a buoyant force to an object that is partially or completely immersed in it. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. So FB equals the weight of the displaced fluid. So I have I guess it's a block of ice. I have a block of ice, and I hold it in my hand and it has weight, and then I put it in the water and it sinks and it sinks and it sinks until it displaces its own weight in water, at which point its weight, 100 newtons directed downward toward the center of the earth, is equal to the buoyant force, 100 newtons directed back up, and at that point it starts to float because the net force on it at that stage is 0. Alright, so I have my raft. It's 4 meters by 4 meters, and it's got some depth to it, 0.3 meters. And it's made of pine wood. If we remember back earlier, we had that table. Maybe I'll click back to it. We had that table of densities. Here it is. So pine wood, pine, yellow pine, 550 kilograms per cubic meter, and I have this thing floating in water. Water has a density of 1,000 kilograms per cubic meter. Alright, back to our example. It's got to be up here somewhere. Alright, so I want to figure out if it's going to float. I don't know. How should I know if this is going to float? And then, if it floats, how much of the raft is beneath the surface? All right, will it float? I guess in a simple sense, I could say, hey, you know what? Intuitively, I have the sense that if something is less dense than water, then it should float in water. I guess that makes sense. What else could I do? Well, I could say, all right, what if I took this raft and I shoved it underneath the water, pushed it under the water so that it was displacing its own volume in water? Would the buoyant force in that instance be greater than or less than the actual weight of this pine wood? So I can figure out the volume of this, 4 times 4 times 0.3 meters. And if it's all made out of pine wood, then I can figure out the mass. And if I can figure out the mass, then I can compare that to how much buoyant force it would experience if it was completely submerged. All right, so the volume of the raft, 4 times 4 times 0.3 is 4.8 cubic meters. Pretend there's a little 3 there. Cubic meters. So the maximum buoyant force that would act on this raft is density of water 1000 times the volume of the water that is displaced by pushing this under the water, 4.8 cubic meters, times the 9.8 meters per second squared acceleration due to gravity, 47,000 newtons. The raft itself, since the density is 550 kilograms per cubic meter and the volume is 4.8 cubic meters, 9.8 meters per second squared, it's got a true weight of 26,000 newtons. If I shoved it under the water, it would displace 47,000 newtons worth of water. Thus, the upward acting buoyant force is greater than the weight and it would float. All right, well, floating's good. That's half the problem. By how much does it float? How deep does it sink before it starts to float? It will sink in the water until it displaces 26,000 newtons worth of water. So our objective is to figure out the volume of 26,000 newtons, and then I can figure out how much of the raft is under the water. So the volume of 26,000 newtons, well, in this case, since we know the dimensions of the raft are 4 by 4, we can say, all right, so the volume is going to be 4 by 4 times this height, this depth that it's going to sink. So I can solve for the height independently and say, okay, 26,000 newtons divided by 1,000 times 4 times 4 times 9.8. It's going to sink 0.17 meters into the water before it's displacing 26,000 newtons worth of water, and then it will start to float. If I then climb on the raft, I will add my weight to the pushing down, so it'll be 26,000 newtons plus my weight in newtons, and it will sink a little bit deeper, and then if I jump off, it'll float back up again, so long as its buoyant force is equal. All right, how much water is needed to float a ship? Well, really just a monolayer of water molecules around it. It's not the water that's important, it's the water that is being displaced. So there's kind of a nifty demonstration we can do in lab sometime where you take a graduated cylinder, so that narrow, tall cylinder, and just add like 5 milliliters of water into it, but then take a wooden dowel that just barely fits inside, and you have this thin layer of water all around the dowel, and the dowel, you can kind of spin it around and see that it's actually floating in the water, even though the volume of the water is nowhere near the volume of the wooden dowel. There's other applications, but that takes us to the end of our Chapter 11 material.